We point our dishes at the void, and something points back. Radio telescopes across Earth catch whispers from depths that shouldn't whisper. Signals that repeat when they shouldn't repeat. Patterns that mock our physics. Bursts that carry more energy than our sun burns in years. All compressed into milliseconds. 12 transmissions haunt the data, each one defying explanation, each one rewriting what we thought we knew about the universe's quiet places. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the SETI Institute and NASA's Deep Space Network archives. Now back to the story. Number 1. The WOW signal. August 15th, 1977. Ohio State University's Big Ear telescope locks onto something impossible. 72 seconds of pure signal from Sagittarius. Jerry Ehman circles the printout data, 6 characters that spell out 6 EQUJ5. The intensity peaks at 30 times background noise. No natural source burns this bright, this narrow, this clean. Ehman writes one word in red ink: wow. The signal matches the 21-centimeter hydrogen line, exactly where extraterrestrial civilizations would broadcast. The frequency sits at 1420.456 MHz. Earth's rotation carried the signal across Big Ear's beam pattern for exactly 72 seconds. The telescope never recorded anything like it before, never recorded anything like it since. Follow-up searches using Arecibo, Green Bank, and Very Large Array find nothing. The transmission vanishes like it never existed. Project Beta scanned the same coordinates for 23 years. Silence. The Harvard SETI team spent 2 decades hunting for a repeat. Nothing. For 47 years, that 72-second window remains the strongest candidate for alien contact in human history. Number 2. Fast radio, burst 121.102. November 2nd, 2007. Parkes Observatory in Australia detects a burst lasting 5 milliseconds. The energy release equals what our sun produces in 300,000 years. Duncan Lorimer's team calls it impossible. No known physics generates this power signature. The burst travels 11 billion light-years from when the universe was barely 3 billion years old. Its dispersion measure of 375 suggests passage through vast amounts of plasma. The signal arrives at multiple frequencies, with higher frequencies reaching Earth first, exactly what happens when radio waves pass through ionized gas. But here's the puzzle. The burst seems to originate from outside our galaxy. 11 billion light-years puts it in deep space, beyond the local group. The energy required to generate this signal would vaporize Earth-sized planets instantly. Most radio sources fade gradually. This one fires like a cosmic gunshot. The detection launched a new field of astronomy. Teams worldwide hunt for similar bursts. They find hundreds, each one more mysterious than the last. But none match FRB 121102's perfect isolation. Most fast radio bursts repeat. This one fired once and went silent forever. The frequency suggests rotation. The intensity suggests collapse. Number 3. The Kepler star. October 13th, 2015. Kepler Space Telescope data reveals KIC 84628552, dimming in patterns that break astrophysics. Normal planets block 1% of starlight during transit. This star dims by 22%. The light curves show asymmetric, irregular dips lasting days. Tabitha Boyajian's team rules out instrumentation error, stellar debris, planet rings. They analyze 4 years of Kepler data. The star shows no regular transit pattern. The dimming events cluster in 700-day cycles, but vary wildly in depth and duration. Some dips last hours. Others persist for days. The star's brightness drops by different amounts, sometimes 2%, sometimes 22%. No known planet could create this chaos. The dips don't repeat. They don't follow Kepler's laws. They mock everything we know about orbital mechanics. One hypothesis emerges that nobody wants to say aloud: megastructures. Dyson swarms harvesting stellar energy. alien engineering on astronomical scales. Wright's team at Penn State calculates the mass required. Billions of Earth-sized objects orbiting the star. The alternative explanations sound equally absurd. Comet swarms would need to be larger than Jupiter. Dust clouds would dissipate in months. Ring systems would show predictable patterns. Follow-up observations from Las Cumbres Observatory confirm the star continues its bizarre behavior. SETI searches for radio signals from the system find nothing. The dimming continues. The mystery deepens. Number 4. The Parkes-Peryton signals. Data spanning 17 years. Parkes Observatory logs dozens of brief, powerful signals from seemingly random sky positions. Each burst lasts milliseconds. Each arrives at different frequencies simultaneously, physically impossible for cosmic sources. Radio waves travel at light speed through vacuum. Lower frequencies travel slightly slower through plasma. Cosmic sources should show dispersion, higher frequencies arriving first. The perytons show no dispersion. All frequencies arrive together. This violates basic physics. The signals appear only during daytime hours, never at night, never during storms. Teams spend decades hunting for the source. Equipment upgrades, interference filtering, geographic correlation studies. They map every peryton to sky coordinates. No correlation with known objects, no correlation with satellite orbits, no correlation with aircraft flight paths. The signals seem random, impossible, mocking. Then in January 2015, Emily Petrov's team installs new monitoring systems, real-time frequency analysis, automatic alert systems, precise timing equipment. They catch a peryton in real time and trace it instantly. The source, microwave ovens. Staff opening the doors before the timer expires. 17 years of data. Hundreds of person-hours. International collaboration, solved by cafeteria physics. The universe's sense of humor runs dark. Number 5. The Vela Pulsar Glitch. December 12th, 2016. The Vela Pulsar, a neutron star spinning 11 times per second, suddenly spins faster. Its rotation period drops by 11 millionths of a second instantly. Pulsars don't do this. These cosmic lighthouses keep time more accurately than atomic clocks. The Vela Pulsar sits 1,000 light-years away in the constellation Vela. It spins 11.2 times per second, every second, for decades. Each rotation sends a beam of radio waves sweeping across Earth like a lighthouse. The timing precision reaches nanoseconds. Then something breaks. The energy required to change a neutron star's spin rate equals the total nuclear arsenal of Earth. Ryan Shannon's team at CSIRO detects the glitch using the Parkes telescope. The pulsar's magnetic field strength reaches 1 trillion Gauss. Its surface gravity is 100 billion times Earth's. The star contains more mass than our Sun, compressed into a sphere 20 kilometers across. The crust consists of atomic nuclei arranged in crystal structures stronger than diamond. Within hours of the glitch, the pulsar begins slowing down again, but it never returns to its original timing. The rotation period settles at a new value, permanently changed. Something inside a city-sized object with the mass of our Sun just rearranged itself. The physics of neutron star crusts can predict small glitches from crystalline fractures, but this glitch exceeds all models. The Vela pulsar contains mysteries dense as its own gravity. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the CSIRO Parkes Observatory and the International Pulsar Timing Array. Now back to the story. Number 6. UY-Scuti brightness variations. Discovered in 1860 by German astronomers at the Bonn Observatory. Located 9,400 light-years away in Scuti constellation. This red supergiant measures 1,700 times our Sun's radius. If placed at our solar system's center, its surface would engulf Jupiter's orbit. The star burns through helium in its core, fusing heavier elements in shells around a growing iron heart. But UY-Scuti pulses in ways that violate stellar evolution models. Its brightness varies by magnitude over periods ranging from months to decades. Variable stars follow predictable patterns. Cepheid variables pulse with clockwork precision. RR Lyrae stars vary on schedules measured to seconds. UY Scuti mocks these rules. The variations don't match predicted convection patterns for hypergiants this size. The star dims for months, then brightens suddenly. Sometimes the changes happen over days, sometimes over years. Some pulses suggest internal structural changes, impossible for stars this massive. Each brightness cycle releases energy equivalent to smaller stars' entire lifetimes. The star masses 40 times our Sun. Stars this heavy should explode as supernovae within millions of years. UY Scuti should have exploded 10 million years ago. Instead, it continues pulsing signals across space that our physics can't decode. Ground-based observations show spectral lines shifting in patterns that don't match radial velocity measurements. Something about this star's internal structure defies our models of stellar physics. Pulsing, burning, waiting. Number 7. The SHGB 0+14 a signal. March 12, 2004. SETI at Home Distributed Computing Project isolates a narrow-band signal near the constellation Pisces. 4 million home computers process data from Arecibo Observatory. The signal appears in the processed data like a needle in a haystack of cosmic noise. The transmission occurs at 1420.4 MHz, close to the hydrogen line, but offset by cosmic motion. The signal appears intermittently over several observation periods. Its strength varies, but maintains coherent frequency structure. The bandwidth measures less than 1 Hz, impossibly narrow for natural sources. Quasars emit across thousands of megahertz. Stars radiate at all frequencies. This signal holds to one precise frequency, like a laser. Dan Wertheimer's team at UC Berkeley confirms the signal doesn't match any known satellite, terrestrial or astronomical source. They check military radar, civilian aircraft, spacecraft telemetry, radio astronomy surveys. No match. The frequency drift suggests a source moving relative to Earth, but the pattern doesn't match planetary or stellar motion. Planets orbit predictably. Stars move in straight lines across the sky. This source accelerates and decelerates randomly. Follow-up observations using Arecibo find the signal region empty. Teams point the telescope at the exact coordinates. Silence. The transmission stops as mysteriously as it started. 300 hours of analysis yield no explanation. SETI protocols require confirmation before announcing contact. SHGB 0+14a, never confirmed. Number 8. The Bloop, May 19, 1997. NOAA's hydrophone array in the Pacific Ocean detects an ultra-low frequency sound. The Equatorial Pacific Ocean Autonomous Hydrophone Array consists of sensors placed 3,000 meters underwater. The system monitors ocean acoustics for research and environmental tracking. At 15 hours 36 minutes, Universal Coordinated Time, multiple sensors detect an unusual sound. The signal rises rapidly in frequency over 1 minute, then stops. Its origin, approximately 50 degrees south, 100 degrees west, near the coordinates of H, P, Lovecraft's fictional Lyrae. Pure coincidence. The bloop's amplitude suggests a source larger than any known whale. Blue whales produce the loudest biological sounds on Earth. Their calls reach 188 decibels and travel hundreds of kilometers. The bloop measures louder and travels farther. The frequency profile doesn't match geological activity, submarine operations, or known marine life. Christopher Fox's team at NOAA's Acoustic Monitoring Project rules out human-made sources. They analyze the acoustic signature against databases of known sounds. Earthquakes produce different frequency patterns. Volcanic activity shows different duration signatures. Military sonar operates at higher frequencies. The sound travels over 5,000 kilometers through deep ocean. No biological source on Earth produces calls this powerful. The ocean's SOFAR channel allows low-frequency sounds to travel vast distances, but the bloop exceeds all known biological limits. In 2012, Scientists attribute the bloop to Antarctic ice movement, massive icebergs grinding against the seafloor. But the acoustic profile still doesn't perfectly match ice-cracking signatures recorded at other locations. Number 9. PSR-J 1903+0327, February 22, 2006. Jodrell Bank Observatory discovers a pulsar with the most precise timing ever measured. This neutron star spins 716 times per second, faster than kitchen blenders. The rotation period measures 1.397 milliseconds, with precision reaching 15 decimal places. Its pulse arrival times vary by less than 15 nanoseconds over months of observation. The precision exceeds our atomic clocks. Atomic clocks drift by microseconds per day. This pulsar keeps time to nanoseconds per year. But here's the anomaly. The pulsar's pulse profile contains substructure that changes systematically. Each pulse lasts microseconds, but contains internal structure lasting nanoseconds. The profile shows multiple peaks within each rotation. The peaks shift position systematically over observation periods. The changes don't match predicted neutron star physics. Standard models predict pulse profiles should remain stable for millennia. Each pulse carries information in its fine structure that our models can't explain. The star's magnetic field strength reaches 10 to the 15th Gauss, strong enough to stop atoms from forming normal bonds. At this field strength, matter behaves differently. Electron orbitals distort, chemical bonds break. The magnetic field energy density exceeds the rest mass energy of matter itself. Something about this pulsar's internal structure generates signals our physics can't decode. The pulsar sits 2,300 light-years away. Its lighthouse beam sweeps across Earth 716 times every second, carrying encoded information from the most extreme physics laboratory in the known universe. 716 spins per second, 15 nanoseconds precision, unexplained structure, number 10. The Pioneer anomaly, data spanning 30 years. Pioneer 10 and 11 spacecraft show unexplained deceleration of 8.74 times 10 to the negative 10th meters per second squared. The force points toward the Sun and remains constant across billions of kilometers. Pioneer 10 launched March 2nd, Towers 1972. Pioneer 11 launched April 5th, 1973. Both spacecraft carried identical designs, identical instruments, identical propulsion systems. By 1980, both probes had passed Jupiter and Saturn. Their trajectories should follow Newton's laws precisely. Instead, both spacecraft show identical anomalous acceleration toward the Sun. John Anderson's team at JPL rules out gas leaks, solar pressure, gravitational effects of outer planets. They analyze 30 years of Doppler tracking data. The anomaly appears in both spacecraft, despite different trajectories and launch dates. The deceleration equals roughly 10 times the gravitational acceleration at Earth's surface. But it acts at distances where solar gravity should be negligible. Thermal modeling suggests asymmetric heat radiation from onboard systems, but calculations can't fully account for the observed effect. The spacecraft carry radioisotope thermoelectric generators, producing heat asymmetrically. Computer simulations show this could create small forces, but the simulated forces change with distance. The observed anomaly remains constant. The spacecraft carry plaques depicting naked humans, Carl Sagan's greeting to alien civilizations. Instead, they broadcast a mystery about our own physics. Something in the outer solar system doesn't behave according to Newton's laws. Later analysis using advanced thermal modeling explains most of the anomaly, but small discrepancies remain unexplained. Number 11. Sagittarius A star's radio emissions. The supermassive black hole at our galaxy's center weighs 4 million times our sun's mass. It sits 26,000 light-years away behind dust clouds that block optical light. Radio waves penetrate the dust. Very large array observations reveal SGR A star as a compact radio source smaller than Mercury's orbit around the Sun. It should remain quiet between feeding events. Black holes only radiate when matter falls into them. SGR A star feeds rarely, maybe once per century when a star wanders too close. Instead, SGR-A star produces regular radio flares lasting minutes to hours. The emissions peak at frequencies that don't match standard black hole physics. Synchrotron radiation from accelerated particles should produce smooth spectra. These flares show sharp frequency peaks that suggest structured emission regions. Andrea Ghezi's observations from Keck Observatory show stars orbiting the black hole at 17% light speed. During closest approach, these stars should trigger massive emissions. Star S2 completes its elliptical orbit every 16 years. At periapsis, it passes within 120 astronomical units of the black hole. But SGR-A star's radio behavior doesn't correlate with stellar orbital periods. The emissions arrive in patterns that suggest internal structure impossible for black holes. Event Horizon Telescope images show the black hole's shadow surrounded by glowing accretion disk material. But the radio flares originate from regions smaller than the event horizon itself. Each flare carries information about space-time geometry near the event horizon that our general relativity can't fully explain. The flares suggest magnetic field structures threading the black hole's ergosphere, the region where space-time itself rotates with the black hole's spin. Number 12, the cold spot, discovered in 2004 by the Wilkinson Microwave Anisotropy Probe. A region of space 1.8 billion light-years across, where the cosmic microwave background radiation measures 100 microkelvin colder than average. The cold spot spans 60 times the Moon's diameter in our sky. Its temperature difference violates inflation theory's predictions for universe-scale structures. The cosmic microwave background shows temperature variations of 10 microkelvin across the sky. These tiny differences represent density fluctuations in the early universe, seeds that grew into galaxies and clusters. The cold spot's temperature deficit exceeds all statistical predictions. Inflation theory predicts Gaussian random fluctuations. The cold spot represents a 6 sigma deviation, probability less than 1 in 10 million. Istvan Sapudi's team proposes a supervoid, a region with 90% less matter than average, might explain the cooling. Photons lose energy climbing out of gravitational wells. A massive void could cool passing radiation, but even the largest known voids can't account for this temperature difference. The Boötes supervoid spans 330 million light-years and contains 60% less matter than average. It produces temperature variations of 20 microkelvin. The cold spot requires a void 10 times larger and 10 times emptier. The cold spot's edges show fine structure that suggests it's not a simple absence of matter. Planck satellite observations reveal internal temperature gradients that don't match void models. The structure shows organization, patterns within patterns that suggest the cold spot formed through non-random processes. In 2017, researchers using the South Pole Telescope find the cold spot contains structure within structure, subregions of varying temperature that form patterns inconsistent with random void formation. The data suggests the cold spot isn't empty, it's organized. Temperature maps show concentric rings, spiral patterns, asymmetric features that mock our cosmological models. Some theorists propose the cold spot represents a collision signature, evidence our universe collided with another universe during inflation. The collision would leave a circular scar in the cosmic microwave background. But multiverse collisions remain speculative physics. Others suggest the cold spot represents a texture, a topological defect formed during phase transitions in the early universe. These exotic structures could produce cooling signatures matching observations. But textures should decay over cosmic time. The cold spot shows no signs of fading. These 12 signals don't connect. They emerge from different distances, different physics, different instruments across decades of observation. The WOW signal originated from interstellar space. Fast radio bursts arrive from distant galaxies. Tabby's star sits in our cosmic neighborhood. The cold spot spans the observable universe. Each mystery operates on different scales, from neutron stars smaller than cities to cosmic voids larger than superclusters. But they share one trait. Each one breaks the models we use to understand reality. The WOW signal suggests intelligence where space should be empty. Fast radio bursts release impossible energies from unknown sources. Tabby's star dims in patterns that mock planetary transits. Pulsars glitch beyond theoretical limits. The cold spot punches organized holes in space-time itself. Our receivers keep catching whispers from depths that shouldn't whisper. Radio telescopes scan frequencies where hydrogen atoms transition between energy states. These frequencies should carry signals from extraterrestrial civilizations, if they exist. Instead, we find signals that don't match any civilization we can imagine, patterns that suggest physics beyond our current understanding, structures that hint at engineering on scales we can barely comprehend. And somewhere in the data, encoded in frequencies and timing and temperature variations, the universe continues transmitting messages we're not yet equipped to read.